Hi. Uh, in, in continuation with the MOSFET circuits, let us consider this circuit having a resistor RD. So there is a MOSFET, so whose W by L ratio is 25. So let us assume the length of this is 10 micrometer. So W for a ratio of W by L of 25 will be 250 micrometer. So then W bell becomes 25. Now the task is we are asked to find what is the value of RD to keep MOSFET at the verge of saturation. So first we should understand, so what is, okay, how long the MOSFET will be in saturation. We know that VDS, that is voltage across drain to source of the MOSFET, has to be greater than VDS saturation to keep the MOSFET in saturation. This is the condition for keeping it in saturation. So what is VDS sat? VDS sat is nothing but VGS minus VTO. So since VGS is given as 0.7 volts and VTO is assumed to be 0.4, so then VDS sat happens to be 0.3 volt. So okay, now this is the voltage what we're talking about, VD, which is also equal to VDS. The voltage that we measured here with respect to ground will be VDS, so that should be equal to 0.3. If it is equal to 0.3, or let me just make this greater than or equal to. If it is equal to, also it is in saturation. If it is greater than VDS sat, then also it is in saturation. So to find out for what value of RD this is minimum 0.3 volts is the question now. Now to solve this, let us write a KVL for this outer loop. So which gives, of course, even though this is written as VDD here, it actually can be replaced by a battery of something like this. So this is VDD of 1.8 volt. So now if I write a KVL here for this loop, considering a current of ID, so can I write the expression as VDD, the applied voltage is nothing but ID into RD plus VDS. Now I can, because I am supposed to find what is VDS, I can now write VDS is equal to VDD minus ID into RD. Now it is known that, okay, given that VDD is equal to 1.8 volt, which is over here, RD I am supposed to find, ID also I don't know, but since we are given the values of W by L, KP, VTO and as well as the VGS, so we can estimate the value of ID for saturation, which happens to be half KP W by L VGS minus VTO whole square. So let us substitute the known values and then find what is ID. So it is 0.5 into 200 exponential minus 6 into W by L is 25 into this is 0.7 minus 0.4 whole square is the value of ID. You can see now it is 225 microamperes. This is ID in saturation, or you can simply say it as ID. Now we know what is VDS, that is now this is the expression. Now since you are looking for this as VDS sat, this is VDS sat, then this, when I replace this by VDS by VDS sat, then this RD will become RD max. So it is VDD minus ID into RD max. So I know that this has to be 0.3 volt. This is known as, of course, this is known to be 1.8, and ID is 225 microamperes, and of course don't put the unit here, so just put the values micro into RD max. If I solve for this, I will get what is RD max. So how do I solve? Let me use a calculator. So let me feed the equation as it is. 0.3 alpha equals 1.8 minus 225 exponential minus 6 into, this is a variable, I'll name it as alpha a. So then shift cal. So now press ENG. So it gives a value of 6.66 kilo. 6.66 kilo ohm is the value of RDMax. So let us go to simulation and then verify the same thing. Okay, this is my circuit. Okay, let me change this to 0.7. That's what is our values, and VTO is given as 0.4 and this is 200 micro. Let us edit this as, so this should be, W should be 25, so that W should be 250 micro. Now what I'll do is, let me sweep this value of R. So for that, all of you know that this I need to replace it by, within floor bracket, some name R VAR. So there's a varying parameter, so I will use dot step 1 space PARAM param. I'm varying a parameter, that parameter is RVAR. So it should be the same name as that I have given here, which is RVAR. Specify the value, so make it from maybe 1K to 10K in terms of 10 ohms. So let it vary slowly so that we can get a proper value. So you are varying this RVAR, which is this RD. Okay, you can also name it as RD for your one-to-one clarification, identification. So this is, you can also name it as VDS. Okay, this is VGS and that is VDD. Now what I'll do, if I run it now, okay, now I have to select one of the simulation command. Let me take it as .op run. You can see now I'm getting the variation of RD starting from, okay, from 1K to I think it is up to 10K. You can see up to 10K. Now let me just do this. Now let me see what is this voltage. So this is the voltage what you're looking at. So this is that voltage. We know that as long as MOSFET is in saturation, the current remains constant. Let me also plot trace current. This is fine. Now you can see this is current. Let me change it to a different color. Maybe red would be better. Yeah, fine. See, now this is the current. If you actually see the current is 225 microampere, meaning that current is a constant, which is MOSFET is in saturation region as long as of course, so as long as MOSFET in saturation, this current remains to be in saturation, which is 225 microampere. You can see after some value, because on the x-axis I have the value of R that is being changed, so that is RD. So at a particular value, this current reduces, meaning MOSFET enters linear region. So at that point, your voltage, that is VDS, will also be 0.3 volt. You can also see one observation is your ID should be exactly at the verge of 225 microampere and this should be at 300 millivolts. So now you can see this is almost close to 224.95 at the verge. You can see the corresponding resistance is 6.68 kilo ohms, which is as per our expectation. You can see this is the expected value. Let me just see this here. Let me also see this VDS. Now you can see this is VDS. So VDS is, you can see here, this is your VDS. So by the time this comes to 300 millivolt, my MOSFET is in saturation. So why that 300 millivolt? Because that's what is this. So that's what we wrote here. So what is VDS sat now? VDS sat is this. So 0.3. So when it is coming closer to 0.3, just have an eye on this. You can see now I'm just keep reducing. You can see now it is going closer to 300 millivolt. So I'm closer to 300 millivolt now. So this is fine. Okay, I'm very close to that. You can see just past it. Now let me just bring it. Okay, let me just take out this cursor totally. Let me just take it only here. Let me just go close to 300. 300 millivolt is here. Fine, can you see here? It is 6.66 kilo ohm, which is the expected value. So this way we can able to do a simulation where I am changing the value of RD through this dot step command, varying it from 1k to 10k with an increment of 10 ohms. So why I varied it up to 10k is because I found in the calculation the minimum resistance required is, of course, when I say RD max, so it is set as RD max, so that this is the resistance maximum, so that MOSFET is at verge of saturation. If the value of resistance goes beyond this, so then MOSFET is in linear, current also reduces. So you are sweeping it from 1k to, suppose assume that you are sweeping from 1k to 5k. Let us see what happens. If you just run it only up to 5k, since our calculation said that you have to go up to 6.6k, that is the maximum value that you should change. If I run it now, see now, this is hardly 1k to 5k. This is keep changing. One thing to observe here is the current has not at all reduced. You can see this is the current, which is 225 microampere throughout from 1k to 5k, and this voltage, whatever VDS you are having, has not gone below 0.3. So it's at 0.63. So meaning that for this resistance from 1k to 5k, the MOSFET is still in saturation region. So in order to make it to go to linear region, this drop should increase so that this drop goes below 0.3. That is, so if you just come down here, see here, wait, just a minute. Okay, something has happened. Okay, fine. See now, if I increase this value more and more, since this is constant, you are looking for this as 0.3. As this is constant, if I increase RD, this product increases, so the overall voltage starts reducing. So earlier this voltage is more. If you start increasing this, then the VDS starts coming down. So the value of RD at which this becomes 0.3 is 6.66 ohms. That's how we can able to analyze the. Let us see the next one. 1 second. Pass this. Okay, how do I pass? Okay, let me just go to next set of the design. In that design we have something like this. We have a different circuit. This is W by L, this is 0.6 volt, this is 1.8, which is VDD, this is VGS, this is again RD. Here value is given as 1.8 kilo ohms. Of course, here the question is what is W by L ratio so that MOSFET is at the verge of saturation. Again, since it is verge of saturation, let me just measure the voltage here, which I say it as VDS. Shall I now write the expression for this outer loop as VDD is equal to ID RD plus VDS for this outer loop. Therefore, VDS is equal to VDD minus ID into RD. But what is ID? ID is equal to half Kp W by L VGS minus VTO whole square. So out of this, I know these parameters, but I don't know W by L. So let me substitute it here. This is now VDS is equal to VDD minus half Kp W by L VGS minus VTO whole square into RD. The moment this becomes VDS sat, then this becomes W by L maximum. So now let us substitute the values here. So it is now, okay, what is VDS sat now? Since your VGS is 0.6 and VOV is 0.4, VDS sat for this problem is 0.2 volts. 0.2 volts. So let me make it 0.2 is equal to 1.8 minus half into 200 micro. You make it as the unknown parameter max. This is 0.2 whole square into RD is 1.8 kilo. So let us not write the unit. So let me just do it. So it is now 0.2 alpha equals 1.8 minus 0.5 into 200 exponential minus 6 into alpha A, which is the unknown parameter, that is W by L, into 0.2 whole square into 1.8 exponential 3. Shift calculate. So I got the value of W by L as 222.22. So let me make it, or let me just write that W by L as W by L max is 222.22 is the ratio. If the length is 10 micrometer, then what should be the width? It should be 222.22 times this. Then this becomes 222.2 micrometer. So let us do the simulation here. Let me go back to the same circuit. Let me slightly modify it. So this is given as, let me take out this, make it as 1.8K. So since it is fixed, so this W has to be, okay, this is again 0.6, and we cannot keep the value of W by L as 25 as in the previous case. Let me vary this. So let me just put that value in flower bracket as W VAR, width being varied. So here I'll come, and the parameter that you are changing is not RVAR, but it is WVAR. You can give whatever name. From where to where you want to change? So let me change it from maybe, since we go up to 2222, let me just vary from 1000 U to 3000 U with an increment of 10 U. So for every 10 micrometer starting from 1000, it will go up to 3000 micrometer. So in this range from 1000 to 3000, I will come across 222.2. So I may not exactly get this 0.2. So what I'll do is, let me just make it only 1 micrometer itself. Okay, this is fine. Of course, it may take some time, but it will be very precise. I'm done. So you can see now we are varying the things here. So let me run. So if I run it now, you can see now it is taking more time. So let me measure only. What I'll do is, let me delete this F5. Okay, it's taking too much of time. Let me stop this and do it using with an increment of 10U. Now you can run. I can see it is coming quickly. Now, what are the voltage that you are looking at? You are looking at a voltage of 0.2. You find out for what W by L, you'll get this as 0.2 because the expected voltage VDS sat is 0.3, sorry, 0.2 volts. So let me look at, so let us just have a look at this. This is 0.2. So at that 0.2, how much is your W bell? Because on x-axis what I have is W bell ratio. So this is enclosed 200 now. Fine. Can you see this? This is 2.22178 milli, which happens to be 2021.7 micro. So which is as expected. So you expected this much. Now actually how much you're getting is 2217.8 micrometer, which is very close. So this is using simulation. This is using calculation. So now it's exactly in the same way as we did in the first problem. The second problem is, only thing is you have a fixed value of RD, you are changing W bell to keep the MOSFET in saturation. So if the W bell goes beyond this 2222, then MOSFET goes to linear region, because this VDS will become less than VDS sat. So that's what we saw here. Can you see this is going below that 0.2? So you can see 125, 153 millivolts, all those things. If the W bell is more than that, you can see it is still in saturation. Sorry, W bell is less than that. So here it is, W bell is how much? It is 160 or 150, something like that. Okay, let us move to one more question, which is